So again, I thank everyone for attending our technical workshop for this afternoon. We are going to have 4 different workshops, talks for today. And this would be the workshop corresponding the lectures that were given last week. Okay, thank you for all of the attendees from the lab and also from our students in the computer science program of the university, and for also for those who are attending from other universities as well. So first off, in our lecture for, not lecture, but technical workshop for this afternoon, the title of the workshop would be the development of camouflage object detection networks. This hands-on workshop offers participants a comprehensive introduction to camouflage object detection. It's a field in computer vision that focuses on segmenting hard-to-spot images in environments. Designed for advanced learners, the session would walk you through end-to-end workflow of developing and evaluating camouflage object detection models. Attendees will be guided through the practical steps of setting up and training camouflage object detection models, followed by evaluation procedures using standard metrics. It will conclude with an analysis of performance through quantitative metrics, helping participants interpret detection results and refine their models effectively. And by the end of this workshop, you're going to have um, a functional camouflage object detection pipeline and gain confidence to apply these techniques to your own projects. Let me introduce to you the speaker. The speaker for this workshop would be Aaron. Aaron Gabriel C. Dichoso is currently a 4th-year computer science student at De La Salle University under the BSMSCS honors program. As a member of our lab, his experiments focus on camouflage crop detection with an interest in pursuing the improvement of CCD, or camouflage crop detection network architecture, for his thesis in pursuit of accelerating agricultural infrastructure in the country. So without further ado, I'll be giving the floor now to Aaron. Aaron, you may start your presentation.
Hello, everyone. So welcome again to our technical workshops for today. I'm your presenter, Aaron, and I'm going to send everyone a Google Drive link for the technical workshop files for COD this afternoon. So just a bit of a recap and a review from last week. Camouflage object detection is actually a segmentation task where we focus on segmenting objects that are hard to separate from the environment. And in here, if you have read the requirements for the technical workshop, I've also asked everyone to download specific versions of Python as well as CUDA. And specifically, I think what's the most important part here is Anaconda, because we are going to be working on making our Anaconda environments for this workshop. Okay. So from my experience, actually, I found that using Anaconda environments for COD is going to be really effective because a lot of COD networks, they are like implementing their own architectures, and like they're all trained in their own custom versions of Python. So just to like help out and to keep everything consistent and to allow our networks to train effectively even without downloading so many versions of Python, and I use Anaconda environments for this. So if you guys have already downloaded this Google Drive link, I will be going through what each of these network directories contain and just the overall workflow of how I train COD networks. So without further ado, let's start. So in here, I have the same directory just installed in my computer. And as you will notice here, we have two notebooks that we are going to go through. First is the data sampling notebook, because our dataset for this workshop is going to be on the COD 10K dataset. This contains a lot of images of camouflage objects. Some are non-camouflage as well. So if you are working on like classification tasks, and mostly there's a lot of camouflage objects of animals, people, etc. This contains a lot of different pictures. So let's just explore a bit here. And as we can see, we have different images here, as well as in here in GT object, this is the segmentation map of your specific object here. So it corresponds to like the contours or the shape of the object that's trying to be segmented away from the image. Aside from that, we also have this. So if you are working on specifically instance segmentation, not just semantic segmentation is what we'll be focusing on today. But you could also use this if you wish to train your own instance segmentation network as well. Aside from that, there's also here just the edges. So it's really a really comprehensive dataset. However, since due to the amount of like different objects in here and just the amount of images, we're just going to sample it for the purposes of this workshop. So in here, how I start the sampling process is I first import the dataset. So I'll just enable my own Anaconda workshop environment here. So for those who are following along and do not know yet how to yeah. So for those who are following along and do not know yet how to actually use Anaconda, you could just install it online and create your own environment using this line here. And then I would name it something like workshop 2, something like that. After that, I actually already have an Anaconda environment prepared for this workshop. So let me just activate it using this line. And we're actually going to use this later on when we're actually training our networks. Okay. Actually, let me just switch this for just to make it easier for us. So I'll just run this. And in here, all is this doing is accessing our specific directory. So this is just accessing the directory here in the datasets. So it is going to datasets, code 10K, and then the training dataset and the testing dataset, because we're going to sample both of those. And then it's also preparing an output dataset for our directory. So this will be sampled, this will be like created later on. Yes. So actually, I could just delete this for now. Yeah. And then we'll sample our own during this workshop. So how I went about sampling the dataset is I first looked at all the different categories that are contained in COD 10K. So I do this by viewing the specific name format of the images. So as you can see here, they all start with COD 10K, then cam, which means it's a camouflaged object. And then 1 aquatic, 4 crocodile, and then this is what I'm looking for. These specific class names, that's what I'm going to use to sample the dataset. So as we can see here, If I were to view this output, it actually gives me all of the different classes that are contained inside content key. And I just do that by recursively splitting the categories using the first I split this category, the names using dash, and then I just append all of the unique categories found into a dictionary. So this is just like a helper function for you to decide which ones you would actually want to include in your sampling dataset. Finally, I just isolated 5 for now, and then I actually start to sample the images here. So I'll just click this for now to actually sample our testing and our training dataset. So how it works is pretty simple. So first, it creates the directory for your sampled images. And then after that, I'm only going to isolate the images that are found that include these specific classes. Once I've isolated those images, I just run random.sample and I specify how many images I want to sample. And then I just copy those images and paste it into my output directory in here. So as you can see, just fairly simple Python code for now. And that is all for the data sampling phase of our content K. Now we can actually move on to the training phase of content K, of our COD networks. So just a review. This is our data sets, and now we are going to use sampled content K to train our COD networks. Our networks that I have included for this workshop can be found in here, the networks directory. And from here, I have included 3 networks that we are going to be working on today. Here we have HitNet, PFNet, and RISNet. And you can find the links of these specific networks in the model evaluation file, a notebook. I have given you links to them if you wish to learn more about how they work. What's important is how to actually run these networks. So all of them have their own specific training file. If you were to open their directories, so as you can see, they all have their own custom code. And what I usually do is I do not make my own code at all when training these datasets. I just modify the code that is already existing in the notebook so that it points to the specific dataset that I want to train on it. And I modify things like the parameters and like the number of epochs, etc., etc. So let's start with the simplest one, I would say first, which is PFNet. So this is PFNet, and I'll just run you through like what each training file would usually contain. So usually you would see something like this, an arguments table or an arguments file. So this just specifies the parameters that you would wish to have in your training phase. So a lot of these are self-explanatory. Epoch num for the number of epochs, batch size referring to how many images per batch you wish to feed in your network. The last epoch, this is when you would wish to like load an existing network into the file. And other things that are maybe important, like save point during which iterations of the epochs do you wish to save your currently trained network, and scale. Scale here refers to how the image resolution of your images whenever you are training your network. So you just modify these like according to your experiments, and once you run them, it will just work as intended. Next, we move on here to the paths. So in here, there's just more of just like understanding the code that was given to you from other researchers. So for example, here, the visualization paths. This is just where I save all of the logs that the training phase wouldn't have. And here, the log path, this is where, yeah, also like more logging, just more logs, just to for you to like uh, keep track as to what happened during the training phase. Aside from that, here, these are like specific transformations that's being performed. So I usually don't touch this because this might be like essential to the training phase or like custom made accordingly to the network. So I usually do not touch this or modify this at all. And finally, here, the training set. So as we can see here, there's um, imports of names of variables in here, and you can find it in the config.py file. So code training root. So to actually view this, I look through like the names and it just corresponds to this file. And there. So here, I've already prepared like the actual directories that we're going to use. So for example, here, this is for a different data set that is also being trained. However, I've added my own variable here so that we can train cod10k. And then I'm using this cod10k training root. And I've also specified where the dataset is located. And finally, I've also specified where the backbone is located. So this is like a specific RESTnet that's being used as part of PFNet. So I've also saved all of them in here just for our convenience in this workshop. But usually you would download this online. These are all like pre-built already. So you just need to like find the specific one you need. Okay. So as mentioned, this is the training route, and all we're doing here is we're pointing it to the training data set, and our this file will just handle it. Nah. So that's actually all that you need to know about this PFNet. So all I need to actually do is to run the code already. Um, what happened? Oh, I ran the code, but I just forgot to enable my environment. So that's just another thing you need to keep track of. Make sure that the environment you're working for is actually enabled for your specific training file. And as we see, this is actually now training the specific network. So it's now training a version of PFNet, and it's all being saved here in the checkpoints folder. Okay. So you could just leave this to run if you can. Sometimes when you are running this and you might get some out of memory errors, that just usually means you would need to reduce some parameters such as the scale, the batch size. And if you want this to run like not too many epochs, you would just reduce the number of epochs here. So you just leave this to train, and then you should get something like this model that I have prepared earlier. So PFNet custom. So we are going to evaluate this later on. But in short, COD training, when you're training the networks of other researchers, just what's important to understand is you just need to understand their like repository, where the parameters are being stored, and for example, like the dataset root, and you just need to modify those parameters accordingly. Okay. Additionally, usually in their repository, they would have like, for example, in here, if we were to go to PFNet, they would also have instructions for you to follow. For example, here, these are like the requirements of PyTorch that they have specified. So these are like specific and custom to every single kind of COD network that you may train. Hence why I usually prefer to train all of these COD networks in their individual Conda environments so that I just don't need to have to think about like any possible incompatibility issues later on. Okay, so if everyone is following along, can I have like a raise of hands or a thumbs up from everyone right now? If it's okay. Okay, thank you. Okay, it's good that everyone is following along so far. So we've already shown you how to train like one network. I'm going to show like a similar process as well with HitNet and RiskNet. However, with RiskNet specifically, we're going to dive into how to view the architecture of the model itself and how to modify it if you need to modify it for your experiments. So let's just have another example here again with HitNet on how to train your models. So in here, I've opened up, usually it's just labeled train.py, and I'll just look for example here, this used to be something called images and GT. So this is like the directories that are being used by the researchers for their dataset. However, if I were to view my dataset right here, the directories for my image and ground objects are different. So I just change that accordingly. Aside from that, I see here on op the test path, I'll try to look for where that is saved. And let's see. So op the test path, control F, and there. So it's actually a parameter that is being passed on. And as we see here, the default value, I've already modified the default value here to point to the training and testing datasets of our sampled content. Okay. Aside from that, you can also see here in the parameters, you have here the epoch number, the learning rate, the type of optimizer, Adam, W, or SGD. Aside from that, other parameters such as the batch size, the training size, and the number of epochs to save, when to save the model according to like every n epochs or something. Okay. Aside from that, I also save like the logs of the training process in here. So that's what like a training process would look like for your COD networks. And aside from that, yeah, more things that I needed to modify in here. So just to like point towards the correct model, the correct directories for our data set. And aside from that, that's all I really needed to look at. So I could now just run this and make sure to run it in the right. Yeah, there we go. It just didn't activate the correct environment again. So this is just going to run and execute. Okay, so it's building it now. And you'll see this just work on the background. If for some reason you would get some like errors, such as like, for example, something is missing or it's using a specific library that you do not have access, you could always just look into, usually they would have something this called like a requirement text file. And this is just going to show you all of the things that you need to install in order for you to use their repository. Okay? Yeah, so this is just training as is. I'll just leave that to train while we talk about our next topic here, which is RiskNet specifically. So for RiskNet, this is a bit different because if we were to view this as is, we can see here an extra parameter. So it needs an image root, a ground truth, and a depth root. So going back to our workshop or our lecture last week, we saw that RiskNet is actually one of the first networks to utilize depth information in their training. So now RiskNet, as it is, requires depth data to work. So what I'm going to show you right now is how I can modify existing architectures so that it can fit our experiments. In this case, I'm going to remove the depth data that is needed by RiskNet so that we can still run the architecture, but without the depth data. Okay? So first, what I did, I just looked for this loader function. So this loader function, this a data loader, and it handles, yeah, just how to get the images loaded into the model during network training and testing. So as you can see here, there's a lot of depth information that's being needed. So all I did there, I just removed it, really, just like that. So remove, 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 remove. And I just continued doing that for all of the functions in here. So this is removed. Oops. Okay. That's not supposed to happen. Yeah. Um, okay. And yeah, I just removed all of those functions in here. Aside from that, in here as well, it's using depth data. So I just removed all of those. And there's more in here. Depth transformation. More in here. So this was one of the functions that was included. So these are all the functions that we just modified earlier. So I'm just going to remove all of the depth data. Okay. And same thing here with the testing dataset. I'm just going to remove, oh, speaking of, I forgot to remove this. And remove the transforms, remove this, remove this. There's no more depth data included. And EG, this is not included anymore. EG corresponds to the depth data here. And that's it. And that's the data loader done. Now we're actually going to modify the architecture itself to remove depth data. So I'll go down here and I'll just going to double check. Okay, we don't need this anymore as well. So all in all, that's all good. Now let's modify the train phase here to also not use that data at all as well. Okay. That I think that's it. Yeah, that's all. So that's the training data, the training phase removed. Now we actually move on to the model itself. So as we can see here, this is the model that it's training. We can import it in model.risnet. So model risnet, and these are all of the model architectures. Okay. So now, if you were to compare this with the in here RISNet node depth. Oh, okay. Yeah, I already removed it. Yeah. So what I did here is this function, this residual feature decoder. This used to have like a really long MFF. Oh, here MFF, multimodal distribution. Okay. So this specific module, as you can see here, it uses depth data, right? And it performs a whole lot of different operations that involve the depth data. So if when I read the literature, it said that in order to test it in models without COD networks, they just disabled this module. So what I did here is I just um, disabled it. I removed all of the specific like operations that it's being done here, and then I just passed it regularly, just like an identity. Just like a forward pass, just a basic identity operation, ganun. Okay. So just highlighting this, just so you could see the differences between RISNet in its regular state and RISNet when modified without depth data. Okay. And just like that, we can now train RISNet as well. So, okay. I'll just activate the file. Okay. And then this is just going to run, and that's it. So we are now running our own version of RISNet that does not use depth data. Okay. And once you've gotten all of these data sets all up and running, you should get the outputs in here. See, I've just prepared my own outputs in here, just like my own networks, so that we can actually see the testing phase as well. So for the testing phase, I'm only going to test one of them, and I'll leave the testing of the other networks to you as like a take-home assignment as well for everyone else. So for testing, you just have to look for the testing file here. That's usually included in the repositories already. So as well as the testing file, they have like their specific operations that's being done. And all you need to really do is to specify the test size, the directory where your model is located and saved, and the dataset directory where your ground truths are saved. That's all you really need to do in here. Okay. And once all of those are ready, you could just run this file. Okay. Just like before, wait lang. Activate workshop. And this is going to run, and it's going to save. Oh, no such file. There's not node depth. Okay. Oh, I just renamed it wrong. So custom.pth. So I just let it point this file right here. And done. It's now running. And it's all going to save all of these results, all of the predictions in here. So these are like the different segmentation maps that I've already tested with our um, pre-prepared networks. Okay, there we go. And once you've done all of that, we can now move on to model evaluation. So model evaluation, it's going to be done here in this notebook here. So all you really need to do is to run these files, and just these blocks of text, these blocks of code is going to handle the visualization and like the metrics computation of your um different networks for COD. So this block, this just gets all of the images inside our dataset, all of the testing ground truths as well inside our dataset. It's all obtained in here. So we are going to use them for comparison with our predictions as well as visualization. After doing so, I just specified the directories where all of these different datasets are located. So all of the predictions, all of the predictions of our networks. And then after that, I just, after doing that, I just got all of the different images located inside each network prediction. Okay. So this is just like a sanity check to check the count of your predictions in the testing data set. More sanity checks just to see that, you've obtained the right images as well. And then finally in here, I'm going to display all of the predictions. So in this utils.file, hold on, yeah, custom. Oh, hold on. Oh, it didn't. Okay. Let's fix that later. But in this utils.display images file, this just contains like a custom made this just contains like the visualization that I use to show all of the different images and comparing them with the ground truth. So I have two types of visualization that I have in here. And let's fix this. Let's see. Why is it not working? Okay. I'll just okay. So I think that it might be because wala siya dito. So let's just restrict this. Oh, I think I trained the wrong. Okay. So it's just pointing to the wrong data set. Okay. But yes, if you were to train it using the it's not pointing because it's using the different sample. Yes. Sorry. Okay. So There's just a bit of a problem here. It's because, yeah, we resampled earlier. That's why when it's trying to compare these results in here, not finding the correct images. So I won't train the other one right now, because you would need to like retrain all of these networks again to actually show the visualization. But just to show you the second visualization in here, this one I'd say works a lot better in visualizing like the differences in your prediction of each network in here, and you can actually see the ground truth in here. So when it's colored purple, that means it's a false positive. It predicts something that's not supposed to be there, in the ground truth. False negatives, it failed to capture those parts, and the true positives are colored in cyan. So just for those who didn't catch why this didn't work, it's because earlier we performed data sampling again. So of course that resulted in a new sample data set that doesn't align with my previous predictions in here. So this is actually predictions from a previously sampled data set. That's why. So in here, I also made it so that you could visualize the predictions according to each class. Okay, so this is the predictions according to the chameleon class. This is according to the cat. This is, yeah, another cat, and oh no, this is the dog, and one of this is the dog and the cat, and the other owl. And now we move on to the metrics computation. So for the computation of metrics, we use this library in here, the PySOD library. So this already has their own implementation of all of the different salient object detection and camouflaged object detection metrics that are being used in research right now. And I use this to compute the performance of each network. So what I do here, I just have a custom function prepared, and all it does, it um, prepares an object that performs the computation of each metric. So the ones that we talked about in the work lecture: E measure, MAE, S measure, and weighted F beta measure. So all of these objects, I feed the ground truth and the prediction pair of each image into the object using this step function. And then once I've done feeding all of the images inside this function, I return the final results. Okay. So you just have to run this function as well. So this function, it's just going to go through all of the networks that you want to evaluate and all of the images contained in there. And then it's going to compute the metrics for each image. And then after that, it's going to get the average across the entire image and place it here in the results. Additionally, it's going to do the same thing again, but class-wise. Okay? So this is usually good if you want to view the performance according to each class, because maybe some objects are better camouflaging than others, or is a much more difficult task for COD, for example. So maybe you'd wish to view the metrics on a class level basis. And all of this gets saved in a CSV file that is contained in the data folder. So just to view the results in here again. Here, these are the networks, and these are the metrics that you can see here. So when with WT here, well-trained, these are networks that are trained on the entire 10K dataset, while custom is only trained on a small sample size of COD 10K. So as we can see here, generally, when we're looking at FWB, okay, we look at FWB for the overall performance of the dataset, of the network, sorry. And as we can see here, when they are trained in a custom dataset, meaning just a small subsample, they have significantly lower results compared to the well-trained counterpart. So makes sense naman, right? Since this is trained on the entire dataset, it only makes sense that it's going to have a higher performance. Okay. Additionally, it also has a lower MAE, so less errors, less prone to errors usually. Aside from that, we can see here that actually for PFNet, all of the other metrics kind of align close to together. So there's not much difference in terms of the other metrics. So this means that for PFNet custom, maybe since it's a low power network, right? And you're just kind of just looking for the shape. If you just want to have it detect like the general shape of the object, maybe you don't need to train it on the entire dataset. Maybe you could just train it on just a small subsample, and it's going to get the shape right anyways. So that's what S here means. S is the shape measure. For E, same thing here. If you just want to get the edges right, you could just train it on a custom dataset for lower performance, because the E measure seems very similar to the well-trained measure as well as the average error. So that's just like a way to read the different network metrics here. If we were to go here to something like this CSV file, maybe it's a lot better to visualize in Excel. So as you can see here, RISNet, this is trained on like a really small sample. So as we can see here, RISNet struggles in the chameleon compared to something like dog, owl, and owl. So what if maybe there's some trends that we can see as well in the other networks? So I think we can see that's an ongoing trend in the networks. So for example, here in PFNet, 4.9 is the score, FWB measure score, compared to 8.2, which is the dog score for chameleon versus the dog score for, the dog score versus the chameleon score. Maybe that trend continues on with HipNet as well. So as we see here, dog usually has a high score versus chameleon with a low score. So maybe that's an indicator that chameleon is generally a more difficult task compared to dog, because maybe chameleons, right, they're a lot more designed to camouflage in their environment compared to something like a dog, maybe something like that. So that's maybe one way that you could interpret these results. Okay. So that's it for our technical workshop. Thank you for listening, and the floor is now open for questions.
Any questions for Aaron, specifically on the implementation side? Maybe we'll take one question from the listeners before we proceed with the next presentation. If you want, you can raise your hand so that you'll be acknowledged, and you can ask your question, or you can send it via the chat. Okay, maybe I'll ask the first question here. Um, I want to see, or we want to see again the visualization that you presented.
Sir.
This one. Yeah, this one.
Okay.
So here we're seeing a lot of, we have predicted the object properly. How about the false positives,
Yes,
false
sir.
negatives? What can maybe, what can we do to prevent having those false positive or false negatives?
Mm. So the false positives and false negatives refer to this pink space that is being seen in here. So first off, for some networks, for example, here in custom, it has a lot of false positives because maybe it was trained on like a really small sample of the data set. So another thing that you could try is increasing like the number of epochs or increasing the number of data that you include. Aside from that, in here for HitNet, it actually really acknowledged this below. I think that's a common trend that we can see here since this is a cat and the print is like all over and the pillow prints are like for cats. So I think this is like a really difficult task for them. Um Usually you would lower the false positives by maybe something like increasing the batch size, increasing the number of epochs or something like that. So it's all about how you would configure. So yeah, like the first thing that you could maybe think of is how to configure these parameters to increase your performance. So higher epochs may mean that your network um, hasn't converged yet. So maybe you could do more epochs. Maybe a higher batch size usually would have higher performance as well. Maybe you could try that.
Okay, thank you. Any more questions? Maybe let's see a raise of hands if you do not have any more questions for Aaron. Okay, thank you. Thank you as well for the presentation, Aaron. We learned a lot about camouflage object detection.
Thank you, sir.
Thank you.